Okay, so the time has come that you've all been waiting for. As you know, this workshop has been an attempt to bring together philosophers and cosmologists, and one of their guests, I think, is uniquely qualified in both cosmology and philosophy, is going to make a few remarks, perhaps unconnected with his talks already. So I was looking hard to think of something to say that would illustrate to you the depths of how philosophers, what they can bring to cosmology. And there was this nice article in the newspaper on Sunday. I don't know how many of you saw this, but let me tell you about this. So this is, it featured the host of Max's talk on Monday to the Institute of the Future, what's it called? Future of Humanity. Nick Bostrom and others. And in this article, it was described how Nick and others had set up an arrangement with an American company to basically freeze their bodies after death, so that in 100 or 1,000 years or whatever, they would then be able to be revived with the new technology and you know, participate in whatever is happening then. So it so happens that the insurance company they contracted with demanded a certain amount for this, and so two of the Oxford academics said, well, yes, we'll do this. We'll go for the whole body option. Nick Bostrom opted for the head only. It was rather less. So I'm curious to know how Max would envisage his future. Anyway, it's a great pleasure that I so Nick, of course, is a philosopher, but that's beside the point. So let me then, with great pleasure, introduce Max Tegmark to make some remarks.
So first of all, I just want to seize this opportunity, since I'm the last man standing here after all the alcohol, to actually, on behalf of all of us, extend a very warm set of thanks to the organizers for putting together this wonderful meeting, which has been really, really fun. Thank you so much. And as I was just discussing with David Wallace here, it's actually quite fascinating how things change in the social climate of science. Hugh Everett, when he first talked about many worlds, he wasn't even allowed to call it that by his advisor. And then he couldn't get a job in physics. And even 20 years ago, people generally criticize it by saying, you know, this makes no sense, and I hate it. And now, we actually discuss it at scientific conferences like this. So that is a remarkable shift, I think. And since many worlds has now become so mainstream that it got more votes than any of the other interpretations here, the organizers decided that they want me to talk about something even more out there, and even less mainstream, an even bigger multiverse. So I've been tasked to spend the next 20 minutes doing that. I guess the idea being that you've now had so much wine that no harm will be done because you won't remember it in the morning anyway. So I'm going to talk about this idea, the mathematical universe hypothesis, or the level 4 multiverse, which I've just written a book on, my first ever book. If you ever know any friends who have trouble with insomnia, it's coming out in January. It's guaranteed cure. Very, very effective, okay? And I think, if I ask myself, what are the most useful ideas ever that have come up in science, in physics in particular, I would say there are two ideas that really stand out. The first one being doing experiments. And the other one being trying to make mathematical models of what we measure. Now, why has that second idea been so useful? This really intrigued people already back in ancient Greece, right? And by the time it got to Galileo, he was so fascinated by this that he even exclaimed that nature seems to be a book written in the language of mathematics. And after that, Newton came along, and special relativity came along, and general relativity, and quantum mechanics just got more and more useful to do mathematical modeling. And Dirac wrote a famous paper in the 30s remarking about how amazing this was. And then in the 60s, Eugene Wigner, in 50s, thank you, I stand corrected, is talking about the unreasonable effectiveness of mathematics in the physical sciences, arguing that this usefulness of math, this usefulness of the second idea I mentioned, is so remarkable that it kind of demands an explanation of some sort. And then the Standard Model was discovered, giving an even deeper level of mathematical regularities. And then the Standard Model of Cosmology came out, showing that even the larger scales were like really mathematical. And then we discovered the Higgs boson, which was predicted with a pencil, right, by Peter Higgs. So why is this that nature is so accurately described by mathematics? Some people will say, it's just somehow we invent things which are useful and it's all in our heads. Many of my colleagues will say, well, somehow nature is approximately described by mathematics. I'm way out on the extreme. And in my book, I argue that it's not just that our universe is described by mathematics, but that it actually is mathematics, in the sense that we actually inhabit a mathematical structure. And I'll get back to talking about what on earth I mean by this in a few moments. If we zoom in at the micro world and we look at things, it's very different from the everyday. Like if you raise your hand if you have a cat. All right. So what properties does your cat have? Say the first few that just come to mind.
It's very elusive.
It's an elusive cat, okay? What does it look like? What's its personality? Black?
Yeah.
What's its personality?
Moderately affectionate.
Moderately affectionate. So his cat, Pedro Freira's cat, has a lot of properties, right, which don't seem mathematical at all, right? But your cat and all of us are made of elementary particles. Now, what property does an electron have? It has the property -1, the property +1/2, the property -1, and so on, which we humans have made up fancy words for. We call them the electric charge, the spin, the lepton number. Now, these are all purely mathematical properties, right? They're numbers, or more technically, they're aspects of group representations. So you could say that the elementary particles, as far as we know them, are purely mathematical objects, in the sense that they actually don't have any properties at all, except for mathematical properties. So if the stuff in our world has building blocks which are purely mathematical, what about the fabric itself, space on the very larger scales? If we zoom out and look at space and time, what properties does it have? Well, space, for example, has the property 3, the largest number of pencils I can put that are perpendicular to each other. We call it the dimensionality, right? It has curvature, given by the rank 4 Riemann tensor, another mathematical object. It has a topology, which topologists study, who are mathematicians. And as far as we know, space or space-time also has no properties at all, other than mathematical properties, and is in that sense a purely mathematical structure. And if we buy into this idea that there is no secret sauce in us, as I certainly do, then if I'm made of these mathematical things in a mathematical fabric, in a sense, I'm a mathematical structure too. And what I'm arguing in the book is, in fact, that our entire physical reality is a single mathematical structure, just a very complex and interesting one, which happens to have some mathematical substructures in it, which are self-aware and are having a nice dinner here right now. Okay, so this sounds pretty whacked out, and I hope you all had some wine and in the right mood for this sort of stuff. Why on earth do I take this seriously? Well, first of all, if you start with this external reality hypothesis, which I really do believe quite strongly in, that there is a reality out there independent of us humans, I feel it's not really optional for me to not kind of go all the way. Why? Well, because I'm a physicist, right? Like all of you, I'm very interested in this pursuit to find some sort of theory of everything, a complete description of this external physical reality, which I believe is out there, okay? But if this external reality is really independent of us humans, then such a complete description of it it must be possible to give that description in a way that is totally free from any human baggage. We always talk about things with words in the English language, like atom, for example. But if I try to explain this to an alien who never heard of atoms, or to a computer or whatever that's very intelligent, I'm not allowed to use any words which it doesn't know. It doesn't know what elusive means, right? Or these other words that you use to describe your cat. However, if you just start with quantum field theory and you solve it, you'll find actually, oh look, there are these bound states here which keep cropping up. Oh, here's another one, here's another one. Maybe I should make up a word for this because it's useful. Let's call this a proton here. Let's call that a neutron. And very often you see this arrangement with 2 protons and 2 neutrons. Let's make up a name for it. Let's call it schmelium. Oh, maybe helium is shorter, and so on. And we invent these words for things, but they're kind of emergent. The things are there, and then the names are just baggage. There should be a description of all that stuff which is independent of any human language. Now, such a description, if it has no human baggage in it at all, it must be a purely abstract description of just some purely abstract elements, just with some relationships, some relations between them. And now I'm sounding a lot like Carlo Rovelli, talking about how relations are really at the heart of everything. And I think the more we talk to each other, the more we realize that we don't really disagree about very much at all. And what I just described here, an abstract set of elements with relations between them, is exactly what mathematicians call a mathematical structure. What does a dodecahedron have in common with the integers? And what does that have in common with a 3+1 dimensional pseudo-Riemannian manifold? They are all this kind of beast, a mathematical structure. The abstract dodecahedron, it has 12 elements. We can call them faces if we want. We can call them schmaces. It doesn't really matter. The only properties they have is that some of these, they have relations between each other. Some faces are adjacent to others. There's a certain symmetry in there, etc. Those are the only properties that the dodecahedron has. The only property that the number 5 have are the relationships with the other integers. The names we give to them don't matter. So if you take this relatively broad view of math, then you're forced, by just starting with this external reality hypothesis, pretty much to say, hey, this external reality is, in fact, a mathematical structure. And John Barrow raised a very interesting objection earlier, before I even kind of started talking about this, saying that one could feel that this is totally vacuous, because sort of everything is a mathematical structure. Couldn't you say that, oh, if I have a theory that really our universe is 7 blue elephants standing on a tower of turtles or something, isn't that a mathematical structure? Actually, no. Mathematical structures have a certain kick to them. They sort of kick back. I spent a lot of time when I was writing this book, developing some algorithms and writing a computer program that just creates a list of mathematical structures one by one and pops them out. And mathematicians spend a lot of time studying and classifying mathematical structures. You can put them in a sort of big family tree. Now, there are 5 Platonic solids. You can't just make up one more. Once you strip away the baggage, you might find that 2 things that you thought were different are actually the same. If you take a mathematical theory like general relativity, then the mathematical structure will be, say, a 3+1 dimensional pseudo-Riemannian manifold and some tensor fields obeying some partial differential equations. It's not so easy to change it in some arbitrary way to do whatever you want. People have tried a lot, it's quite hard. And mathematicians, it's very telling, I find, when they refer to what they do, usually don't say that they're inventing mathematical structures, but that they discover them. So, if we take this point of view for a moment, that actually we are part of this purely mathematical object, we don't honestly know which one it is. Of course, that's why we're having this conference. We don't have quantum gravity yet, so we certainly are not just living in a pseudo-Riemannian manifold because we need quantum mechanics. It might not be living in some Hilbert space with some operator algebra either, because we're not sure what the quantum gravity theory is. But suppose there's some mathematical object We haven't yet figured out which one it is. And somewhere in there is this conference is going on. What does that mean? What implications would it have? Besides being a good excuse for us to drink and be merry and discuss it after dinner. Well, it actually fundamentally changes the way we think about a lot of stuff in physics. A lot of concepts like randomness, like initial conditions, like complexity, we're forced to think about it very, very differently. Because in a mathematical structure, there is nothing random at all. It's completely defined. In a mathematical structure, there is no undefined initial condition. It's all completely defined. There's nothing undefined about the integers, for example, or the cube. And there's also, and we already talked about this, actually, it came up, interestingly, in a different context in this meeting, how even if there is no fundamental randomness, as long as if you can have any kind of cloning, it's going to feel random to that observer. And that's what Simon Saunders and I, for example, were discussing in the many worlds context. Even though fundamentally randomness is an illusion, it feels random to those of us who live in that structure. Initial conditions is a little bit similar. There, rather than the initial conditions telling us something arbitrary or whatever, they are just, the initial conditions we measure are just telling us part of our address in this mathematical structure. So just like measuring that there are 8 planets in our solar system tells us which solar system we're in out of many. A lot of the other initial conditions we measure, like what the Planck satellite looks like and stuff in its data, tell us where we are in this object. And finally, a lot of the complexity, as I also alluded to, all those enormous numbers of bits, 10 to the 89 bits of our universe that we could in principle try to measure, also might tell us mainly where we are in this structure, which itself might be so simple that you could describe its equations just on one t-shirt, which maybe one day will be on sale here in Oxford. Another implication of this, which is more radical and therefore very appropriate for an after-dinner speech, is it forces us to further expand our ontology. Because if this mathematical universe hypothesis is true, then that means physical existence and mathematical existence are really the same thing. And if you have a mathematical object and things in it feel like they're living in a physical real world, as long as they are complex enough to feel anything, then there's nothing special about our mathematical structure. Any other mathematical structure which is complex enough to have something self-aware in it is also going to be a physically real world to its inhabitants. So you can imagine this Platonic realm. Julian Barber, your website is platonia.com, right? Where there are all these mathematical structures. And each one of them is then its own universe or its own level 3 multiverse or whatever. And these different worlds don't exist in space and time. Platonia doesn't exist in space and time, but space and time exist in some of those mathematical structures. In this one, for example. And you might object, well, you might say, I believe that, or someone might say they believe that our universe is perfectly described by mathematics. But still, that's different from saying that it is mathematics. But I object to that, actually. Because if you have some physical stuff which is perfectly described by some mathematical structure, that means that there is an isomorphism between the two. There's a one-to-one correspondence between every entity in the physical thing and every entity in the mathematical thing that respects all of the relations. And if mathematicians have two structures which are isomorphic, guess what? That's their definition of them being the same mathematical structure. There's no meaningful way in which they're different. This is sometimes discussed as the identity of indiscernibles in philosophy. And okay, so suppose we have this vast reality, this level 4 multiverse. What's it like? Well, if we start going out in the most pedestrian multiverse, the one that just comes from inflation going on and making a really big space, much bigger than we can see, big enough that we start getting sort of duplicate conferences going on, right? And those other level 1 parallel universes, the laws of physics are still the same, so we would still learn the same things over there in physics class and discuss the same equations in our conferences, but we would learn different stuff in history class, because in those places the particles started out in different places because inflation gave different different fluctuations initially. In the second level, you could have, as we mentioned in the conference, different effective laws of physics. It might still be loop quantum gravity that rules, or string theory or whatever, but the symmetry is broken in a different way. Maybe as in John Barrow's book, there's a different number of quarks, or some forces are different. So you'd learn different stuff in physics class, in the elementary physics class, but in the advanced physics class, where you learn what the true physics theory was, string theory or whatever, you would learn the same still. In the level 4 multiverse, even though its fundamental equations would be different, because you're actually living in a different mathematical structure. So it's the most diverse of all of them, if you like diversity. Let me just lubricate my throat.
Increase the mathematical coefficient of friction.
Yes, exactly. So, I don't want to keep you for too much longer. I want to just take a little step back here and say, well, okay, is this good news or is this bad news? Well, I think it's good news, actually, for two separate reasons. First of all, if we're curious about knowing more about the full extent of reality, it's good because it gives us opens up a second front for us. In addition to studying the full reality with telescopes that cost ever more and are ever bigger to look farther and farther away, we also get a second front because we can also study the whole thing as mathematicians and just say, okay, let's try to classify all mathematical structures and then see, okay, where are we in all of this stuff? Another piece of good news, I think, is to do with the future of physics. Because if I'm wrong, and there's something intrinsically unmathematical about reality, that basically means that physics is ultimately doomed. We're going to, at some point, if we keep advancing, hit a roadblock beyond which we just cannot proceed. We'll try to make more mathematical models, and it all fails. There just are no mathematical regularities anymore to be captured, and we're stuck forever. But if I'm right, then there is no roadblock at all. Everything is in principle understandable by us, and we're only limited by our own imagination. And I think that would be awesome. So cheers.